I was born ready. Okay, 3. All right, here we are on May 3rd, 2018, spring semester in a jam-packed, standing room only, Burchard 118. So good evening, everyone. As always, I want to thank Sean and all of our SITTV colleagues, which would include Matthew and Jesse, and I hope I'm not forgetting anyone, but thank you one and all for taping this. This is the 3rd one you've done for D4 this semester, and you've done 4 for circuit. So you've done 7 sessions, so thank you. All right, let's get started. What I'd like to do is let you know I posted the final exams. Mirror, they should now be on the course website. I posted the final exams that we're going to look at, and in particular, I thought we'd look at the spring 2014 final exam. I think that's a good one to look at. So this exam should be posted along with the solutions. Now, a question I typically get is, do we get formula sheets? Yes. How do I know what the formula sheets are? You'll see them at the end of this exam. I think they're at the end of the solutions. So I used pretty much the same formula sheet. So if you're concerned about what the formula sheet is, just look at the posted exams. So let's take E232 final exam, spring 2014, and they're posted on, this exam is posted on the course website. Okay, so I hope you find this review helpful tonight. I'm looking at the solutions. Okay, let's not look at how we solve it yet. Let's see if we can read the problem together and see if it makes sense. You're given a sensor, which is a first-order system. Perfect. I got it. The input to this sensor is a constant applied at t equals 0. And the constant is 55 for t greater than 0. Now, the initial reading of the sensor is minus 12.7. Time constant is given. Determine the value of the sensor 11.3 seconds after the constant input has been applied. Okay? Now, I'm hoping you're looking at this saying, oh, I got this. This is not going to be bad. So I like to just graph it. Okay? Okay? This is V out, and this is time. And it says here that the constant input is a value of 55. And my colleagues, what do I know about a first-order system? That it eventually gets to the final value, okay? And it starts at the initial condition. So the initial condition is minus 12.7. Minus 12.7. It go to asymptotically rise and asymptotically approach 55. Now, what do I want? The 11.3 seconds into its journey, 11.3 seconds into its journey, I want to know this value. I'll put an X. That's why it's a little bit too big. You might think I want a big X. I just want the value of X, the unknown. What is the value of the output? Okay. So, in fact, you know what? I shouldn't put X. I should put Y of t. Okay? Because we're about to use notation that says the output is Y of t. So if you don't mind, this is Y of 11.3 seconds. I'm sorry to confuse you, but that's actually the more precise notation. Sean, am I writing large enough? I can write even larger? Got it. Sorry about that, my colleagues. Okay. Okay. We start here. We asymptotically approach. And this is Y of t, which is the output. And we're looking at the value, let's call it here, 11.3 seconds. And I want to know what is that. Okay. Thanks for the feedback, Sean. All right, so I come down here. And I'm hoping, my colleagues, that you know this now very well. For a first-order system, the solution is the homogeneous plus the particular. And the homogeneous is ke to the minus t over tau. And since the input's a constant, the particular solution is that constant. So we get the equation that describes this circuit is ke to the minus t over tau plus k1, which I call the particular solution. And I say, oh, I know the particular solution. That's the steady state solution. That's the final value. As we drew on the graph, that is 55. So what we get is y of t, ke to the minus t over tau plus 55. Now, I'm all set to go here, except I don't know k. You know how to get k. I know you do. You get k by setting by using the initial condition. So the very next line is going to say y at t equals 0 equals minus 12.7. And then we're going to solve for k. So let me just slide down, and I think we're all set. So we get minus 12.7 equals the unknown value k, e to the minus t over tau, that's 0 because t is 0, then plus the particular solution, which is the input. So if my math is right, and I hope it is, because if it isn't, I've graded every other exam wrong from the spring of 2014. So I hope my math is right. We get k equals minus 67.7. And we're almost there. The last thing to do is say, okay, we want to know the value of the sensor at t equal 11.3 seconds. I put in 11.3 seconds, and if, again, my math is right, 49.2. Part A, done. How do we do? Not bad, right? Too easy, isn't it? Yeah, I know, it's too easy. I have to make it harder. Okay, so that was part A. I still see one or two colleagues writing. I'll give you another moment. Sam, help me out. Can I scroll up a little bit? Yes. Oh, this. Right there. Got it, Sam. Besnick, how are you? Pretty good. I'm doing good. Why wouldn't I be? D4. D4 and soda. That's it. I'm happy. Huh? Any more plans after for this evening? I actually have so many more emails to do. A lot of colleagues are sending me emails. Besnick, that's my life right now. Exams and emails. Could you work on something to automatically, using artificial intelligence, respond to my emails as if I would do it? Oh, Besnick, if you did that before the final, you'd get an A. The final is like only 7 or 8 days away. It has to be proofed and perfect. All right. Ah, look at this, Kristen. There's a part B. Ah, okay. Now, determine the time it will take for the sensor to reach 90% of its value. Now, the only thing you need to know, Awa, is that 90% of the final value is 90% of 55. Okay? Because that's going to be the final value. So, if you didn't know that, you could go back to the solution from part A and let t go to infinity. And if you let the solution with t go to infinity, you'll see that the final value is 55. Just as we drew over here on the graph. So I say, excellent. I think we're in good shape. I now look at this and say, this isn't too bad. So I want to find out 90% of 55. Turns out to be 49.5. Now, I plug it into the same equation we derived in part A. We know that it's ke to the minus t over tau plus the right-hand side, in this case 55, the final value. K is minus 67.7. So I just go through it and I solve for t. We're given tau, by the way. Tau is given in the problem. So I get down to here. And by the way, does it concern anyone that t is a negative number here? Is this? No. Why not, my good colleague? Very good. We have the natural log of a fraction, which itself is negative. So I'm very glad there's a double negative here because we get positive time. Okay. So I plug in the value for tau, and we get 11.5 or so seconds. And just because I had nothing else to do, I decided to double check it. And I say, good, that's part B done. Excellent. All right. Just giving my colleagues here time to write everything down. Okay, now who can I see out there in the home audience? Sarita, I see you. Now, who do I see from I see, look at this. They're all together in the same row, all the Kappa Sig brothers. They're all sitting in the same row watching this. This is amazing. All right, who do I see in the afternoon class? I see Mr. Real Madrid, Juan. He's very happy his team is in the European Championships. Okay, so I see all of you out there. See, we have Internet of Things here, too. This camera is magical. All right, so that's it. We got it all copied? All right, good. Now, this is the next part of the problem. We kind of jump ahead into chapter 11. Okay? Now, you don't have to prove this. You just have to know it. All right? So it says here, the input is now disconnected. The constant input is disconnected. And we now have a ramp. Okay? So now we have a ramp input to a first order system. Now, let me ask you a couple of questions I didn't ask here, although it's kind of implied. If I have a ramp to a first order system, do I have a steady state error? God bless. Yes. Yes. Ramp input to a first order system, steady state error. Great. How about a sinusoidal input to a first order system? Yes. Okay? All right, so here we're asking for a ramp input. Way to go. Ramp input. Now, determine the time delay in the indicated measurement. So I'm going to walk over here to just draw a graph that I'm going to feel that you're pretty comfortable with. Wait a minute, camera. I'm sorry to drive you crazy. I left my marker here. Okay. Okay. All right. All right, so this is time. Now, this is the input, okay? And it has a slope, rise over run, A over 1. So the equation for this line is A times T. That's now the input. Now, what do I know with the first order? I know I have an error. So it turns out that after we have some exponential rise, we then want, I'm not drawing it very well, it's supposed to be in parallel. So from beyond a certain point, these two lines, the upper and the lower, are meant to be in parallel. So now notice the response of the first order system always has an error. And it's always also lagging behind. Okay, so those are the two things I'm going to ask you about. So here it says, what's the delay? So I say to myself, what do you mean by delay? So this is the true value of what you're trying to measure. When does the first order system give you the true value? It's going to give it to me sometime later. So I kind of just draw this over and say, that's when I get the true value. Okay? So I look at this and say, there's a lag. There's a time delay. And it turns out, it was proved in the book, and we discussed it in class, that time delay is tau. So that's the time delay or how much I lag behind. So it's tau. Now, you don't have to prove it. I just want you to know it. I just want you to know that there's a steady state error and it's tau. Now, help me out. The next question I can ask you is what's the instantaneous error? Okay, so what's the instantaneous error? The instantaneous error is this is the true value. This is what I'm reading. Okay, the difference here is the error. Anyone remember what it is? A times tau. Excellent. A times tau. You know what I did one year? You're going to think I'm terrible. I said the equation has a slope of the line ST. You know what I got for the error? A times t. We never defined a in the problem. Wasn't that terrible of me? That was. So don't memorize AT. Memorize it's the slope times tau, because I might say the slope is S. Then if I get AT, I'll say, gee, I don't know where you got that from. Okay? So it's the slope times tau. All right? I think that's the next question. I think. Yes. Instantaneous error is A times tau. All right. All right. Okay. That takes care of problem one. We're all good? Too easy, right? Sorry about that. All right. Now, this is the Chapter 7 problem. This is the Chapter 7 problem we did. Okay? We have done this problem in class, just slightly different arrangement. But so this is a valid Chapter 7 problem. Okay? This is a high priority problem. All right? All right. So while you're reading it, I'm going to draw it on the board. And let me erase all of this. Okay. All right, so we're given a system, remotely measures air quality, and reports it to a central control station. The remote sensor is connected to a wireless network. So I say, okay, I'm going to draw this out. So we have sensor. Then we go into a wireless network. So I'm just going to put down NET for network, okay? And let's see, wireless network, and the received signal is then filtered. So then we go through a filter. We go through a filter, then we amplify. So we have a big amplifier, and then we go through an analog to digital converter, and out comes the reading. All right? Now, what this question asks is, what is the plus and minus value on the reading? Now, I like this problem because it ties it all together for me. I can understand that the error in the sensor, the wireless LAN, or the network, the amplifier, the A to D converter, the filter, they all add up. So this looks at the addition of all the errors. Okay? So now, as I'll show you below, the only thing you have to do to solve the problem correctly is to take your time and read it carefully. And then put everything, as I'll show you how I do it, underneath the appropriate blocks in this diagram. So I met with a lot of people regarding exam 1. I know you're not going to make this mistake again, but just to make sure, it says all of these factors here are a certain percent of full scale. Okay, full scale. And I tell you that the range on the instrument is from minus 3,000 to plus 3,000. Help me out. I have a long drive home. I want to smile. What is full scale? Sean? Sorry? Right. In fact, just 3,000. Just 3,000. Okay? The range is minus 3,000 to plus 3,000. The full scale, Mira, as you know, is the largest number. Sam, you know this. So it's 3,000. Okay? It's 3,000. Now, You might say, Professor, did we cover sensitivity and linearity and hysteresis? I would say, well, maybe not. Okay? It was in Chapter 2. I didn't cover everything in Chapter 2, but I know you probably read it because you were so interested. But even if you didn't, these are systematic errors. That's all I need to know. These are systematic errors. All right? So I say, okay, so I'm given a lot more information here. So let me tell you what I did here. I don't want to. Let me write it all on the board so you can see it kind of being developed. Here, the range is 3,000. So, by the way, my handwritten note, systematic, that won't be on the final. You got to know that. Okay, the handwritten note, Kristen, you got to. This is systematic. So let me jump ahead. Sensitivity, linearity, and hysteresis. Here's what I'm going to show you on the next slide. 0.25 over 100. Why? Because it's percent. Times 3,000 is going to be the systematic error for sensitivity. So let me just jump ahead to the next slide. Oh, no, I have to jump ahead 2 slides. They're making it hard on me. There we go. There. Okay? So these are the systematic errors. And where do they belong? You might remember, for those who attended the lecture, for those who didn't, I'm sorry, you didn't give me a chance, but you might be watching this now. So here we have the bias error, capital B. So I look at this 0.25 over 100 times 3,000. And I do this for all 3 numbers. So underneath the sensor, I have a bias error of 7.5. I have another bias error of 4.5. And I have a third bias error of 3. And I got all that just from the problem, the given information in the problem. All right. Now, I jump back and say, okay, I think I got everything out of the first 2 paragraphs that I can. I'm now down to the 3rd paragraph. Says here, a large number of auxiliary tests. What that means is I didn't do these tests. The manufacturer did. And they probably did like hundreds of them, if not thousands of these tests. So the manufacturer of the sensor did a large number of tests, and they found out that the standard deviation of these measurements is 4.3. So standard deviation brings up probability. Probability brings up randomness. So this is a random error. And the random error is associated with where? The sensor. Okay? So this is called the standard deviation. So standard deviation is 4.3. Okay, so far so good. Now, let's go down to the next paragraph. I say, all right, the next paragraph. For the wireless network, someone did tests there, and they got a standard deviation of 1.7. So I say, okay, we got a standard deviation of 1.7. Now, if in reading the problem we see no mention of a bias or systematic error, don't worry. That means it's assumed to be 0. Or assumed to be so low, we're not going to worry about it. So that takes care of the network. And where am I here? Separate test of the filter, we got a standard deviation of 1.3. So I come over here for the filter, standard deviation of 1.3. All right. Now, I'll leave the A to D converter go for just a moment. The amplifier has a standard deviation of 1.5. Okay? Now, the author tries to trick us, so I followed his lead. The A to D converter produces a random uncertainty of 2.5 for 95% confidence interval. What strikes me is every other saying was standard deviation, standard deviation. This says random uncertainty. So the random uncertainty which is P, equals plus and minus. Does anyone happen to remember? T sub alpha over 2 times the standard deviation S. Does that strike a bell? Okay, Kristen gives me the nod. We're good. We're good. So I say, excellent. I got it. Now, I'm making one measurement. So the square, some of you may remember that this is over the square root of n. But I'm making one measurement, so Mira, this becomes 1. So I'm just going to erase that so I don't get confused. Now, I'm assuming the author, in fact, it tells us here. The designer of the A to D converter says 2.5 for 95% interval, confidence interval. I'm assuming, maybe I should have written this down, that this is based upon a large number of tests. I'm measuring 1, so n is 1. But someone worked on this for quite a while and did a lot of tests. So I'm saying, okay, how do I convert P to S? I need to know the T value. I need to know the T value for 95%. Now, I know we did this. I'm feeling I should just do it one last time for old time's sake, just to make sure we can do it. So, Mira, what I'm going to assume is that the manufacturer made a lot of separate tests to determine that the random uncertainty is 2.5. Okay? With that in mind, I'm now going to go to Chapter 6. Oh, in fact, shouldn't I have it here? Yes, I should. I don't. Oh, not to worry. Not to worry. Student T table. All right, now, Sam, 95%. That means the 2 tails is 0.05. This is a single-sided table, so I look up the column, that's 0.025, right? 0.05 divided by 2. Sam? Here's what the author reasons. Even though we have a large number of measurements, you're saying we can use Gaussian. And the answer is, if you use Gaussian, you're going to get the same answer that I'm using here with you. Because we're going to now let the degrees of freedom go to infinity, which means we made an infinite number of measurements. That's going to give us the same answer as Gaussian. So the author says, look, for all of Chapter 7, sometimes we're less than 30, sometimes we're a lot. Let's always use the student T. Okay. Sam, was that okay? So what we're going to do now is we're going to say, okay, I need the one-sided tail to be 0.025, which is here. And what I'm now going to do, as Kristen knows, we're going to let the degrees of freedom go to infinity. Now, you might say, wait a minute, you're only making one measurement. That's right. I'm only making one measurement. But the manufacturer of this A to D converter made a lot of measurements to determine that P was 2.5. So I look here, and Sam, this is exactly the number you would get using the Z table. I get 1.96. God bless Besnick. We get 1.96. So what I can then write is that S equals P over what am I doing? I'm having a freeze here. Yeah, this is right, isn't it? So now we're going to use 1.96. And the author says, look, you can use 1.96, but come on. It's the end of the semester. It's the final exam. 2. Okay, we're going to use 2 instead of 1.96. I can tell that makes you very unhappy, but we're going to use 2 instead of 1.96. So what we get then is 2.5 divided by 1.96, but why don't you go ahead and use 2? So 1.25 divided by 2 gives me what? Oh, 2.5 divided by 2 gives me 1.25. Did I do that right? 2.5 divided by 2 is 1.25. Did I make a mistake, my colleagues? Am I okay? We're good? Huh? Yeah. Okay. I was nervous. I thought I might have made a mistake. All right. So with all of this, my colleagues, we now get 4.3, 1.7, 1.3, 1.5, 2.5 over 2, which is 1.25. At this point, we have done all the reading of the problem, and now we're going to solve it. I think it's easy. I think it's easy. So let's go now. I asked this in multiple parts, so let's make sure now that I can answer the first part correctly. Determine the random uncertainty. Okay? So the standard deviations are going to be the way to get that. So I take all the values of S because those are the measure of randomness, right? Using the standard deviation threshold or the standard deviation definition. So I look at all the S's and I say, okay, I'm going to add them up. Does anyone remember in Chapter 7, how do we add? Right. Right? We're going to square each one, add them up, take the square root, RSS. Okay? So we square, reading it backwards, square, sum, take the square root. So I say, okay, where did you do this? I'm saying the next page. There we go. So we square each term, add them up, and then take the square root. So the random, now this is the standard deviation. This is the standard deviation. Is this the answer to the question? Sam, you're right. It is not the answer to the question. What we were asked to find is random uncertainty. What is the random uncertainty? P. Now, we're asked to find it for 95% with a large number of measurements. I bet you it's 1.96. Right? So T sub alpha over 2 is 1.96. And Matt, with your permission, we're going to round it up to 2. So we take the value of S, 5.185, and go to multiply it by 2. And if we've done it right, we got 10.37. All right. That's part A. How do we do so far? Please.
Are we assuming also there's only one sample here? Is that why you don't have to overroot n?
Exactly. So the question is, are we only making one measurement here? Exactly. So that's why that's why n is 1 and the square root of n is 1. What's subtle here, what's a little tricky, and I hope I've explained it well, and please give me feedback. I, as the customer of this network, is making one measurement. The manufacturer of these devices is making many. So they did that in their testing facility. So that's why when I go to the student T table, we slide down to the last row and use the degrees of freedom equal to infinity. Did I do okay on that? So there's two sets of measurements going on here. Great, thank you. So that's part A. And now we continue on to part B. Determine the systematic uncertainty. Now, the systematic uncertainty, the author uses the letter B for bias, because a systematic error is always a bias. So once again, this S stands for standard deviation, not systematic. Standard deviation. I hope you're okay on that. Matt, did I do all right on that? The B is for bias. So I look here, there's only these three numbers. So what's the total bias or systematic error? We add them up. How do we add in Chapter 7? RSS. So we add using RSS. And now we get the value of the bias error. The last part of the question, if I remember, is to determine the total uncertainty. Now, the total uncertainty is the bias plus the random uncertainty. So we're going to add them together. You know what I'm going to ask. How do you add them together? RSS. Perfect. We're going to add them together using RSS. So we square each term, add them up, and then take the square root. That's the answer. All right. I think that's the second problem. We're good? All right. Now, by the way, I don't know what I was thinking. I don't know what I was thinking. I give you a network of sensors. Couldn't I have just said the probability of a sensor working is 0.8? Did I do that? No. Why? I don't know. I said the probability of sensor 1 working is 0.8, probability of sensor 2 working is 0.8. I don't know why I did that. I have no excuse. It must have been late at night. That's all I can think of. All right? Either that or very early in the morning, which I don't think happened. I think it was more like really late at night. All right? So, here. I know you know this, but since this is our last time together, and Sean is nice enough to record this, let me just do this one last time, the little secret to solving a network of sensors. And I think if you know this secret, and if you take your time, there's nothing I can throw at you that you can't get. All right? So, suppose you have two sensors in parallel. Now, you come in, you come in, you come in, and then you start going out. Perfect. Now, suppose the probability of a sensor working is P. Let's leave it at P. Now, what's the probability of this system working? All right. Now, how does this system work? It works if both sensors work, if the top sensor works and the bottom doesn't, if the top doesn't but the bottom does. Now, you can figure out those three probabilities and add them together. I think that's crazy, because I can give you 5 sensors in a row. Not in a row, in parallel. That's going to be, you have to think of all combinations. No. The secret is figure out the probability that it doesn't work. And then the probability that it works is 1 minus. Okay? So, what is the only case where this system of sensors does not work? Both paths don't work, and they're independent. So the probability of the upper path not working is 1 minus P. The probability of the bottom path not working, since they're independent, I just multiply them, is 1 minus P. So the probability of the system of sensors not working is 1 minus P, that quantity squared. what's the probability of this system of sensors working? Exactly, Sam, 1 minus this. So the probability of this system of sensors working is 1 minus the quantity, 1 minus p squared. Now, I'll give you a moment to copy this down. Just want to have it on the board in front of me here. I think I've drawn this correctly. 1, 2, 3, 4, 5, 6. So it's just going to be repeated applications of what we've discussed. So let me now flip this back. I now want to go counterclockwise. And all right, it's just going to be repeated applications of this. So let me know if this makes sense. The probability of sensor 1 not working, 1 minus p, 0.02. Same for sensor 2 not working. And now the probability of sensor 1 and sensor 2 not working is 1 minus p times 1 minus p, which is 0.2 times 0.2. Okay. So that means the probability that we have at least that pair, some combination of at least one path working is 1 minus that. So the probability of, this grouping of sensors 1 and 2 working is 0.96. Have I done okay? Now, it's going to be the same for the other two. So likewise for 3 and 4 and 5 and 6, we're going to get 0.96. So I'm wondering if this might help just to make sure you're okay. We can now, pardon me, we can now erase this and put a single sensor where the probability of working is 0.96. And we can do the same thing here. We can put another sensor here where the probability of working is 0.96. And likewise down here, we have the probability of the sensor working here, the 2 in parallel is 0.96. So we're almost done. I think we're doing pretty good. Now, what's the probability of the upper path working? For the upper path to work, both of these new sensors that we've combined have to work. We've got to get through both parallel paths. So that's going to be 0.96 times 0.96. That gives us 0.9216. Now, what's the probability of the lower path working? 0.96. So now, I think I made this too easy. We now have reduced this to 0.9216. Now, what's the probability of this not working? 1 minus 0.9216 times 1 minus the probability of 0.96. That's the probability of it not working. What's the probability of it working? Exactly 1 minus that. So is that what I wrote here? I hope I did. Okay. So it's 1 minus 0.9216 times 1 minus 0.96. I get a rather small number, and then I just take 1 minus that. That's problem 3. How do we do? Sam.
The one on the test was a lot harder.
Because I knew you were better than the class of 2014. Not bad, huh? Not bad. Now watch, someone's going to, from the class of 2014 is going to watch this, and I'll be getting emailed. I was only kidding.
What are some exams you know that there were examples that we should go over that were more difficult?
I mean, what I would suggest, Sam is asking, are there more difficult examples? Here's what I would suggest. I think you got the basic building blocks. I believe in study groups. That got me through college. If you're studying with someone, why don't you make up your own problem and see if you agree to the same answer? Chances are you're right. Sam, what do you think? Sam, I'm not going to give you the answer to this, but just a thought question. If I had n sensors in parallel, and don't say the answer, not 2, not 3, n, could you tell me the probability of the system working? And then I would ask you another question. As n goes to infinity, what is the probability of that system of sensors working? Don't say anything. Just give it some. Those are some alternate questions that I might ask in various forms. Sam, did we do okay? All right. All right. All right. My colleagues, I'm wondering if I can ask your permission to do something. This is a binomial distribution problem. Can I ask your permission to not put a binomial distribution problem on the final? I think it's unanimous. All 173 people. No, wait. There's someone in the Kappa Sig row who's not raising. We'll let it go. So it's 172 to 1. I think is it almost unanimous? Can we let the binomial distribution go? Okay, we don't got to look at this problem. Okay? So once again, because I'm going to get emails, and the emails are going to be, Professor, can you confirm that there's no binomial distribution? Here's what I'm going to do. I'm not going to answer those emails because I'm confirming them now. I confirm, I pledge my honor, that there will be no binomial distribution problem on the 2018 final. If you send me an email asking me to confirm it, F. Only kidding. All right, are we good? So no binomial distribution. So that means I don't got to do problem 4. Parameter estimation. See, I think this is important because of our IoT lecture. IoT told me a key thing today is big data analysis. And believe it or not, parameter estimation is important. So it's one of the tools, one of the many, many tools of big data analysis, and we've covered it in this course. So I am going to ask you a parameter estimation problem or so on the final. So I'm hoping you're okay with this. So you got a wireless sensor, part of probably an IoT network, and you test 4 sensors. And these are the transmit power for each of the 4 sensors in milliwatts. Estimate the mean of the population and the 90% confidence interval on the mean. Now, you know this. What's important about 4? Less than 30. That means we're using student t. So I say, okay, I get the average. I add them up, divide by the number 4, which is the number of sensors we have. I got the average. Next, I calculate the standard deviation. Excuse me. Standard deviation, the formula is given on the exam. The key thing I want to point out in the formula is that for the standard deviation of the sample, you divide by the degrees of freedom, not by n. So it's n minus 1. That's clearly mentioned in the formula, but just to emphasize it here. So how do I calculate the standard deviation? I take each of the 4 points, and one by one, I subtract the mean and square. I then add them all up, divide by n minus 1, and then, I know it's falling off the page there, that's the square root, raised to the 1/2. You take the square root. And now we get the standard deviation. Now, I think this parameter estimation, I think is pretty easy. This formula is the critical one. It's given on the formula sheet. So we wanted 90%. That means the area of the tails of the distribution is 0.1. Since we got a single-sided student t table, the area on the one tail is 0.05. 0.05. Okay. So let's just make sure that you are all comfortable with this. Student t table, n is 4. So the degrees of freedom, let me slide this down so I can get a little better. The degrees of freedom is 3. Okay, so we look up the degrees of freedom. Now that was what? 0.1 divided by 2 is 0.05. So we should get 2.353. That should be what I have in my solutions, if I haven't messed things up here. And going to the student t table, that's exactly what we get, 2.353. You just plug everything in, and you get an estimate of the population mean using the student t distribution and 90% confidence level. All right. That's our 5th problem on the exam. We skipped problem 4, if I remember, on the binomial. All right, good. Let me pause. We're more than halfway through. How are we doing? All right. All right, so this is a question that looks like it's on chapter 4, maybe chapter 5. I kind of view chapter 4 and 5 as, even though the author has it as 2 chapters, they're very closely related in terms of topics. So you're given a function as shown here. the two highest frequencies in this term, in this expansion, is noise. So I want to get rid of the noise. So we're going to convert this signal f of t to a digital signal using A to D. Now, notice what I wrote in the key, my colleagues. I think the author did this also on one of the homeworks. It's usually sine or cosine 2 pi ft. So just be careful. If I say, for example, the first term is 5 times sine of 375 pi t, you have to set 375 pi t equal to 2 pi ft. And you find out that f is half of 375 because of the 2 pi. So we get the frequencies for each of the terms that I've listed above, 187.5 and so on for each of the 4 terms. Now, part A says, okay, for some reason, that's not a good reason, you do not use an anti-aliasing filter. So you apply the whole signal to the A to D converter. If you apply the entire signal, all 4 terms, to the A to D converter, you got to sample at twice the highest frequency. So you got to go to the frequency of the highest term, or the term with the highest frequency, pardon me, find that frequency and multiply it by 2. So the term with the highest frequency is 1375. So the minimum, absolute minimum sampling rate is 1375 times 2. Sean, you look very thoughtful. Are we okay? I look like, okay, good, good. Now, the signal is now applied to an anti-aliasing filter before going into the A to D converter. Select the cutoff frequency. Now, I've met with, again, a lot of you to discuss this on exam 1. This is a discussion we've had in class and also for those who have come to me. The top 2 terms are noise. So I want to get rid of this term here that has a frequency of 936.5, and I want to get rid of this term here that has a frequency of 1375. Now, the simple way to do it, but it's not the best, is to pick the corner frequency of the filter to equal the highest frequency of the signal you want to get through. So what's the highest frequency signal you want to get through? 637.5. So we go ahead and we select the corner frequency to be 637.5. Now, as I've discussed, I think in my lectures and also for I think almost everyone who's come to see me, I've at least, I think, raised this issue, or maybe not with everyone because some of you got it right on the exam 1. Frequency, gain. For a perfect low-pass filter, we get this response where at the cutoff frequency we drop down to a gain of 0. That's not what happens. It turns out that what happens with a first-order filter is you start to drop. And at the corner frequency, you're down to 1 over the square root of 2, which is 0.707. So we've lost about 29% of the good signal. So what we typically want to do is pick the corner frequency to be a little higher. Okay? So you want to pick the corner frequency to be, let's say, f sub c prime. That means we're going to wind up here. So now I draw this, and notice I stay higher here. And now I drop off. And I say, that's really good. I get a lot more of the good signal. What's the problem? There's always a trade-off. What's the problem? Somewhere over here is F noise. You see the filter with the lower cutoff frequency lets fewer noise, lets less noise through. So if you decide to move the corner frequency further out, what do you also typically decide to do? Exactly. You increase the order of the filter. Okay? So what you do is you say, okay, I'm going to stay high, come down here, but then I'm going to drop quicker. So what does that have to do with this problem? God bless. I think I gave the simple answer, but I said there's a more complicated answer. The simple answer is make the corner equal to the highest frequency you want through. Problem is I'm only getting about roughly 70.7% of that out. So note to TAs. A better answer is to be a little higher than F sub C. But don't get too close to this signal. That's the one you don't want to get through. So I just wanted to share this insight with you. I think it's an important insight in terms of networking design. Besnick, we're good? I move on now. What's the minimum sampling frequency of the A to D converter? The trick is the minimum sampling frequency of the A to D converter is always minimum 2 times the highest frequency that comes in. Now, Besnick, help me out. This brings up an even more subtle point. Besnick, suppose we chose F sub C prime to be whatever that number is. Notice we still get higher frequencies out above that, right? It doesn't drop to 0. So there's another subtle point here. This is theoretically correct. Tell me the highest frequency, multiply it by 2. But in reality, the highest frequency is not the corner frequency. Of course, you're still getting frequencies out a little higher. Okay. So what you would want is if we approximate, and that's the key word, if we approximate the highest frequency by the corner, we multiply it by 2. Typically, what do we do in practice, in real design? We are going to pick a higher sampling rate because I still have higher frequencies. So Besnick, what we might do is to analyze this and say, you know what, I'm going to find out when I'm down to, let's say, 5% of the signal gain. And that means beyond that, I still have frequencies, but they're less than 5% of the good signal. So at that point, I'll say, okay, I'll sample at that rate. You see? So my colleagues, this rather simple system is pretty subtle to think about designing, and that's what I wanted you to think about. Have we done okay on this? All right. A related question is number 7. Ah. All right. Question 7. Let's see if we can figure it out together. What is it asking? You have an n-bit analog to digital converter. I say, wait a minute, time out. What does that mean? Every sample is converted to n bits. The highest frequency is F sub H. The sampling rate of the A to, now this is, I worded this as carefully as I can, so make sure you're okay. The sampling rate of the A to D converter is 1.5 times the minimum required. Now, what's the minimum required? 2 times f sub h. So what's the sampling rate? 1.5 times 2 times f sub h. Because we oversample. Determine an expression for the number of bits generated with a duration of capital T seconds. Now, this may sound difficult. I don't think it is if you follow the units. So let's be very careful and be strict about the units. So the minimum sampling rate is 2 times f sub h. What are the units? Samples per second. Now, the real sampling rate is 1.5 times that. So 1.5 times 2 times f sub h. That, again, is in samples per second. Now, next thing. We have an n-bit A to D converter. Each sample is converted to n bits. So I say, okay, we then have n bits per sample. So, Matt, I see you nodding your head. You know where I'm going with this. You then multiply those two quantities. And I wrote the units down here. All of this, as we discussed on top, is samples per second. And n is bits per sample. I multiply everything out. I get bits per second. Now, what are we looking for? The total number of bits in capital T seconds. Just multiply it by T. How do we do? Intently taking notes. I still see some people writing. We have 2 more problems to go. 2 more problems to go. And then I have some summary comments to make sure you got the right game plan to succeed. All right. So, okay. All right, a filter design problem. I can virtually guarantee something like this. This is important. So this is test 1. I got a feeling for those of you who came to see me who redid test 1, I think you probably well understand this and so on. But let me just go over the highlights. We have a sensor connected to a filter. The filter is low-pass Butterworth, which means we're going to use a certain formula on the formula sheet. And it's nth order. That's the unknown. Okay. Now, what are we told? The sensor provides an output signal of up to 2,000 hertz. We should pick a number a little higher than 2,000, but for this problem, let's pick 2,000. So we pick the corner frequency of the filter to be 2,000 hertz. Now, we want the gain. So let me go back and read the problem with you to make sure you and I are in sync. The third line down, a noise signal of 12,000 hertz is also present. Next to last line, the objective of the filter is to reduce the noise signal by at least 45 dB. That's a loss, so it's negative 45. Don't make it positive 45. That's a huge gain. We want a loss of 45, so it becomes minus 45. So I look here and say, excuse me, we want the gain of the noise to be minus 45 dB. Now, to use the formula I'm about to get to, the gain has to be in non-dB. So to use the formula for the Butterworth filter, I need non-dB. So the gain is minus 45, and the formula for converting to a gain in non-dB is given in the formula sheet and also here. So minus 45 equals 20 times log to the base 10 of G. Solving for G, you get 5.62 times 10 to the minus 3, which is a number less than 1. That's good. We want something less out for the noise. And at this point, you know everything. You just got to plug it into the formula on the formula sheet and solve for n. Now, on exam 1, a number of colleagues had the wrong numbers here. I think a few had them inverted. Make sure you know what this formula means. It's F over F sub C. F is the input frequency. F sub C is the corner frequency. So we want the gain to be 5.62 times 10 to the minus 3 at the noise frequency. And the noise frequency is 12,000. The cutoff frequency is 2,000. I'll leave the math to you. I have it here step by step. I'm sure you'll have no trouble doing it. Now, the last thing, I think 1 or 2 colleagues may have done this on exam 1. 2.89, you don't truncate, you round up. Even if it's 2.1, you got to round up. So 2 point anything, you go up. So the answer is 3. We're good? One last problem. The last problem is another topic that I would like to have on the final, I think. It deals with loading error. Before I do, any other questions? We're good. We're good. All right. All right. So you have a sensor that has a Thevenin equivalent model of V sub t and RT. And you go into a 2-resistor attenuator, and the output voltage is taken across resistor R2. A load resistor is placed in parallel across R2. Determine the loading error. So that's what we have. We have a sensor that can be modeled by a Thevenin equivalent circuit. We have a 2-resistor voltage attenuator. And we take the output across R2. Now, my colleagues, the concept of loading error, I want to make sure you got this. If I measure the voltage with the circuit as it is now, I'll measure V out. If I now put another resistor in parallel with R2, it's putting a load. Think of a beam, you now put weight on it. You're now putting a load on this circuit. The output voltage drops. Now, we typically do not like that because we designed this circuit to give you like an output of a certain voltage. And now because you start adding external resistors, that's going to change. We want the loading error to be as small as possible. So the loading error is the voltage before we add that last resistor minus the voltage after. So V before minus V after. And we're going to use, in this case, voltage division, and we're done. Okay? So, V out before is R2 over R1 plus R2 plus RT. That sets up the ratio times V Thevenin. Plug in the numbers, we get an answer for V before. Now, help me out. I'm now going to put a resistor right over here where currently it's open. What's the only thing I have to do differently? Kristen knows. Help me out, Kristen. Perfect, Kristen. Thank you very much. We do an REQ. And I do an REQ because voltage division requires everything to be in series. So I take an REQ. So what we now do is we have this load resistor. So the first thing is, as Kristen mentioned, it's product over the sum. Hopefully you remember that mirror from the good old days of circuits. How could you forget? So I now get an REQ. And I now do voltage division. And I say, voltage division, it's now REQ over REQ plus R1 plus R Thevenin times V Thevenin. And I think that's what's up here, my colleagues. So that's the ratio we just discussed. So V out is now approximately 9 millivolts. Up above, it was like, 10.6, 10.7. That's the loading error, the difference between the two. So V before minus V. Look at this. I dropped an E. I don't know where it went. Can I? No, okay. So it's V before minus V after. And we get the difference between the two, which is right around 1.63 millivolts. That's it. We're done. We are done with calculating the loading error. We don't have any extra credit. I've gotten tough. All right. Now, I have a few more comments to make. First of all, give me feedback. How did we do? All right. Now, here's what I would like you to do. I know your time is limited. My time is limited. We're all under pressure, so we're in this together, if that's of any comfort. Let me get an eraser, and suppose we were making, it's on the floor. Suppose we were making a game plan for victory. The game plan for victory on the E232 final for spring 2018. I would encourage you do the final exam we did tonight without looking at the solutions. So you can get this done. Secondly, do quiz 1 and quiz 2 from our semester. Now, at the time of this recording, quiz 2 is not yet available, given back to you. At the very minimum, I'm going to post solutions. Okay? So make sure you can do quiz 1 and quiz 2 from this semester. I think this gets you through chapters 2 through 7. My next concern is chapter 11. There were 2 tables. So if you attended class, you know what I'm talking about. If not, find out from a colleague. There were 2 tables that summarized chapter 11. There were also I bet you if Caroline was here, she would know. Caroline, there were some in-class examples. I think there were 2 from Chapter 8. Caroline, I think, is nodding her head, so I think it's 2. Okay? So go over the in-class examples and go over the homework. Oh, Sam, do you want me to go over the last homework problem? Okay, we have a request to go over the last homework problem. Oh, I'm sorry, exam's closed. That's it, we moved on. That's okay. Let me just finish my thought and we'll go. That's true, I will. No, I would never hate you, Sam. How could I hate you? We've been through the wars together in 2 courses. And I know your name now. Right?
I mean, you knew it at one point, and then you forgot it.
See, she has to bring this up. You see, I forget her name, and she couldn't just say, oh, yeah, you've learned it. No, no.
You remember to wear the right belt and shoes, though.
Yeah, I know. Sam once told me, she gave me a fashion critique. See, this is why I don't need IoT for fashion. I have Sam. Sam told me, no, you have to wear the same belt with the same shoes. So I went home and told my wife, and now we're all stressed out. We're making sure all the belts. I told my eldest son this. I know you're listening to this going, what is he talking about? I told my eldest son this. He goes, yeah, Dad, didn't you know that? That's why I had all these belts. And I'm like, oh, I see. I missed all that. Whatever the education was, I missed it. So you got a question on the final and the homework. I'm going to get to both. Let me just finish my thoughts. We're good? Okay. Now, the last thing, see, this gets you through Chapter 7. Then we went to Chapter 11. And then we went to IoT. Now, the best way to study IoT is to sit with someone else, thumb through the lecture notes, and just ask questions. You know, what is IoT? Identify and describe 2 applications of IoT. What's an embedded system? What are the steps in IoT? You might remember that very busy chart we had. If you look at the orange up on top, it's collecting the data, sending the data, storing the data, analyzing the data. And what was the last one? Excellent, visualizing the data. Those are the kinds of questions I'm going to ask you. So that would be my game plan, the IoT lectures number 4, for the final exam. Now, Sam, I'm with you. You have 2 questions, and I want you to leave here tonight as a happy customer. So you said you had 1 question on the final. Help me out.
Well, my question was going to be, you told us in class today that there's going to be part 2 questions on Internet of Things, but you just answered it. So
We're good. So we're down to 1 question.
assuming everything you just listed is stuff we need to know about IoT, which is good.
Good. Now, it's not, may not be a complete list.
I know.
Okay.
But it's a starting point. And then just the third question on 11.13.
Okay, I don't remember exactly, but I remember looking over the solutions. So my colleagues, we're now shifting. And if you want to leave, you can. Sean is great. He's going to keep the camera rolling. We're going to answer this one last question, Sam. Anybody else have any other questions on the final before I switch to 1 homework problem? All right. Sam, E232, homeworks, my solutions, current solutions. This is Chapter 11 solutions, right?
Yeah.
Which problem?
11.13. The third one. That one. Then it was ramp response, and then I didn't understand where to put it.
Oh, you know what? If I remember this, Sam, help me out. If I remember this problem, the author derives it. We don't have to. This is the one we spoke about on the exam tonight. You have a first order system. The input's a ramp. If I remember, they asked 2 questions. What is the lag or the delay? And what's the instantaneous error? The author derives it. So all we need to do, Sam, is, and I remember doing this problem, so help me out if I'm mistaken. All you got to know is the time delay in a first-order system with a ramp input is tau. Right? Now, what is the error? So, Sam, you can just write down tau for the delay. And I think the other thing that was asked is what's the error? The error is A times tau. And this problem, the units were in seconds and minutes, so you had to convert. What was A? Okay, hold it. 10 degrees C per minute. And what was tau? All right, so here it is. Now, I don't know if the units are, help me out, times, it should just be degrees Celsius. It's the error. Right? Minutes with minutes, seconds with seconds. The units should just be degrees Celsius. And it should be 100 divided by 60, so I think it's 1.667. And the units are degrees. Am I right? Yeah, the author says it's minus. Don't worry about minus, because that's whether you subtract the real from the, don't worry about that. Just give me the 1.67. Sam, did I do it? My thanks to Sean and our SITTV colleagues. I think they deserve a round of applause. My colleagues, my thanks to you. I'm sorry for those of you who are relying only upon the videos to get through this course or the reviews. You never gave me a chance, but that's life. It was your decision. For those of you who showed up, you brought me great joy. For those of you who didn't, c'est la vie. All right? All right. Thanks, everyone. Good night.